In this lecture, we will focus on bathymetry, which is the measurement and mapping of seafloor depth. Bathymetry is essentially the underwater equivalent of topographic mapping on land. By mapping the shape of the seafloor, scientists have been able to reveal major ocean features, understand geological processes, and transform how we think about the ocean basins. Bathymetry refers to the measurement of water depth and the mapping of underwater topography. Just as elevation describes the height of land above sea level, bathymetry describes the shape of the seafloor below sea level. Although we cannot see the seafloor directly across most of the ocean, bathymetric maps allow us to visualize underwater mountains, valleys, ridges, and trenches. Bathymetry matters because the shape of the seafloor influences many ocean processes. Ocean basin structures help scientists identify plate boundaries and understand how the seafloor forms and changes. Bathymetry also affects ocean circulation by steering deep currents and influencing how water moves through ocean basins. Without bathymetry, much of modern oceanography would not be possible. As we discussed in the previous class, the earliest bathymetric measurements were made using a lead line, which, as you recall, is simply a rope with a heavy weight on the end. Sailors lowered the line until it reached the seafloor and measured the length of the rope that was released. This method worked only in shallow water and was slow, imprecise, and of course impractical for deep ocean measurements. As a result, for centuries, knowledge of the seafloor was extremely limited. Mapping the seafloor is challenging because the ocean is vast, it's deep, and of course it's difficult to access. Most of the seafloor lies thousands of meters below the surface, far beyond the reach of direct observation. This means scientists must rely on indirect methods to measure depth and map underwater features. A major breakthrough in bathymetry came with echo sounding, also known as sonar. In this method, a ship sends sound waves down toward the seafloor. The sound reflects off the bottom and then it returns to the ship. By measuring how long it takes for the sound to return, scientists can calculate water depth. This technique made it possible to measure depth quickly and repeatedly across large areas. Early sonar systems measured depth directly beneath a ship using a single beam. But modern multi-beam sonar systems send out many sound beams at once, and that allows the ship to map a wide swath of the seafloor at a single time. This allows scientists to create detailed, continuous maps rather than isolated and individualized depth measurements. Bathymetric mapping revealed that the seafloor is highly structured. Scientists discovered mid-ocean ridges, deep-sea trenches, and countless of underwater mountains that we refer to as seamounts. These discoveries showed that the ocean floor is dynamic and geologically active. It's not flat, and it's not featureless, as it once was believed to be. We will talk much more about seafloor topography later in the semester. Bathymetry played a critical role in the development of plate tectonics theory. The global pattern of ridges and trenches revealed by seafloor mapping helped scientists recognize the plate boundaries. Although we will explore plate tectonics in more detail later, it's important to understand that bathymetry provided key evidence for this theory. But not all bathymetry is measured directly with sonar. A newer technology uses satellites to get extremely precise measurements at the ocean surface. Satellites can estimate seafloor features by measuring small variations in sea surface height caused by gravity. Underwater mountains slightly raise the sea surface above them, while trenches create a small depression. This indirect method allows scientists to map large areas of the seafloor efficiently. Let's take a look at a few examples here. On the left is an isoline map. This uses contour lines to connect areas of equal depth. Just like elevation contours on a land map, closely spaced lines indicate steep slopes, while widely spaced lines indicate gentler terrain. Isoline maps are useful for precise depth comparisons. The second image is a color-shaded bathymetric map. Here, color gradients represent depth, with warmer colors indicating shallower areas and cooler colors showing deeper regions. This format makes large-scale patterns easier to see at a quick glance. The third image is a three-dimensional perspective view, which exaggerates vertical relief to help visualize the shape of the seafloor. While not always perfectly to scale, these views are helpful for understanding spatial relationships among features like ridges and trenches. And then finally, the satellite-derived bathymetry uses subtle variations in sea surface height caused by gravity to infer seafloor features. This method allows scientists to map vast areas of the ocean where direct sonar data are limited. Together, these maps show that bathymetry is not just about collecting depth data, it's about how we represent and interpret the seafloor. Although bathymetric maps have transformed our understanding of the seafloor, they do have important limitations. One limitation is resolution. Some areas of the ocean have been mapped in great detail using multi-beam sonar, while other regions, especially remote parts of the deep ocean, are still mapped at much lower resolution. Another limitation is coverage. Large portions of the seafloor have never been directly mapped with sonar and instead rely on satellite-derived estimates, which are useful but unfortunately less precise. Finally, bathymetric maps represent the shape of the seafloor, but they do not tell us everything. They do not tell us the type of rock that makes up the seafloor or the type of sediment. It also doesn't tell us the age of that rock or that sediment. And it tells nothing about the biological communities that live on the seafloor there. So the key takeaway is that bathymetry is a powerful tool, but it works best when combined with other methods, and it continues to improve as new data are collected. Bathymetry remains important because understanding the shape of the seafloor underpins many areas of modern ocean science and decision making. For example, bathymetry feeds into important scientific models. Accurate seafloor maps improve our ability to model ocean circulation, plate boundaries, and long-term geological processes. Without detailed bathymetry, many large-scale Earth system models would be incomplete. We also have to worry about natural hazards. Bathymetry helps scientists understand where underwater volcanoes, earthquakes, and landslides occur, and how these features influence hazards such as tsunamis. The shape of the seafloor directly affects how energy moves through the ocean. More so today than any time in history, we are now exploiting more marine-based resources. Activities such as offshore energy development, cable placement, and potential seabed mining all depend on accurate bathymetric maps to assess feasibility and risk. And finally, widespread ecosystem management has never been more important than it is today. Seafloor topography influences habitat structure, biodiversity, and species distributions. Bathymetry helps identify critical habitats and informs conservation and management decisions. Together, these examples show that bathymetry is not just descriptive, it is a foundational tool that supports science, safety, and stewardship of the ocean. To close, it's worth connecting bathymetry to something many of you may have seen in popular science media. The National Geographic series, Draining the Oceans, creates a dramatic visualization of the seafloor by removing the water digitally. But those images are not fictional. The foundation of these visualizations is bathymetric data, much of it collected using multi-beam sonar and satellite-derived measurements. Scientists first mapped the shape of the seafloor, then used computer models to reconstruct what the ocean basins, ridges, trenches, and shipwrecks would look like if the water were removed. What you see on the screen is essentially bathymetry translated into a visual form that is easy to understand. This is a powerful example of how scientific data are used not only for research, but also for communication and education. This image on the screen shows an example from an episode where they drained a section of the Pacific Ocean, and you can see not only a few shipwrecks, but you can see an airplane that unfortunately crashed in that part of the Pacific. The key takeaway is that bathymetry allows us to study and visualize parts of the Earth that we cannot directly observe. And that same data can support science, safety, and public understanding. In upcoming lectures, we will build on bathymetry to explore seafloor processes and plate tectonics. But before doing that, we need to take a trip into the center of Earth and explore the details of Earth's core. This will then give us the information and context needed to understand seafloor processes and how the ocean basins evolve.